All right, so let's keep talking about the Chandrasekhar or something like that limit. Okay.
You pronounce it much better than most of my names.
Oh, cool.
Yeah.
Cool. I like that. Yeah. All right, that makes me feel happy. I do my best. Okay, so degeneracy pressure, and then Chandrasekhar limit. Where are we here? Yeah, the Chandrasekhar limit. Chandrasekhar limit. Chandrasekhar. I gotta spell it right. Of course, how you spell it's a little arbitrary because it's just a transliteration, basically. As I told everybody, the median wasn't where I wanted it, so I'm adding, it's not reflected here, but I added 0.3 to everyone's score. So mentally add 0.3 to your score, and that's what'll show up in the grade book. And there are solutions posted on Blackboard. So, okay, so we talked about the mass-volume relationship, the mass times the volume of a white dwarf is a constant. And as we've said, seems to imply that V goes to 0 as M goes to infinity, but of course, no, we don't really expect to be able to add as much mass as we want to our white dwarf. I mean, eventually it would shrink below its own, what's the name? Schwarzschild limit and become a black hole. All of a sudden I couldn't think of that word. Schwarzschild limit and become a black hole, but that doesn't happen. Something happens well before that. But that's not going to happen. There is a maximum mass. There's actually a maximum mass for a white dwarf, above which it becomes dynamically unstable to collapse. Those are the magic words. Dynamically unstable to collapse. It becomes impossible for gravity to keep up with pressure because, of course, as we know, in any star, even a dead star like a white dwarf or a neutron star, why, you've got a battle between the inwards pull of and the outward push of pressure. And here we get a situation where pressure ain't going to be able to keep up anymore. Gravity's going to win and make the thing collapse. So let's talk about that. As I've already hinted before, it comes down to the fact that there is a speed limit on how fast the electrons can go. What's the ultimate speed limit on how fast anything can move in our universe? Speed of light, right? And so eventually the electrons become relativistic, and that's what causes the problem if you want to think of it like that. So let's consider the classical speed of an electron having the Fermi energy. I say classically because in quantum mechanics, right, things don't really follow well-defined trajectories, yeah, blah, 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 blah. But if we imagine the particle as a classical particle and calculate its speed, let's look at what we get. Consider the classical speed of an electron having the Fermi energy. of an E minus, an electron having the Fermi energy. So we would say, okay, 1/2 times the mass of the electron times V squared would be equal to the Fermi energy. So notice I'm already, I'm making the assumption that 1/2 mv squared is the kinetic energy, which of course is not strictly speaking true, right? In other words, according to Newton, this is the kinetic energy, but the relativistic expression does not look like that. But let's just look at what the Newtonian speed of that electron would be. It's got the Fermi energy, and we say that's 1/2 mv squared. And so that's going to say, if I solve for V for that electron, well, that'll be equal to 2 times the Fermi energy over the mass of an electron, square root, because I've solved for V squared, and I get 2e Fermi over m of the electron, take the square root of that, and then we'll put in what we had for the Fermi energy into this. And so what you get when you put that in is that this turns into h bar squared over the mass of the electron squared times 3 pi squared times the number density to the 2/3 power. That was our expression for the Fermi energy if we then multiply by 2 over the mass of the electron. And we're taking the square root of all this. And then we put in what the number density was that we developed last time in terms of Z over A and rho over the mass of a hydrogen. And so this becomes h bar over the mass of an electron, because we've got h bar squared over m squared to the square root. So I can just pull the whole thing out to the first power. And then this is going to turn into 3 pi squared times Z over A times rho over the mass of a hydrogen atom, all to the 1/2 power. And now we'll do an example. We'll put in the numbers for what might be the most famous white dwarf, or at least it was the first one that was really recognized as a white dwarf. I haven't mentioned this in class, but do you know what that is? Seriously, when I ask this question, what might be the white dwarf that I'm thinking of? Sirius B, as a matter of fact, yes. So what's the brightest star in the sky?
The sun.
Very good. I tried to get you and I failed. Excellent. What's the second brightest star in the sky? Sirius, as a matter of fact, yes. I've surely, well, at least some of you, you've heard this terrible joke a student told me once about star walks into a bar. Do you know what I'm talking about here? Star walks into a bar, says to the bartender, "I'm the brightest star in the night sky." Bartender says, "Are you serious?" Okay, so Sirius B, let's put in for Sirius B, which when astronomers in the 1800s did the math, looking at its orbit and stuff like that, and calculated from its brightness and all, what its size is, they're like, what? This can't be. But of course, now we know it can be. For Sirius B, actually, I can't remember what year it was that came out, that they're like, wait, we can't believe that this star is really that small and still has that much mass. For Sirius B, whose mass, based on the orbital dynamics with Sirius A, the one that we actually see with our eyes, its mass is 1.053 times the mass of the sun. So it's actually almost exactly the same mass as our sun. Now our sun is a white dwarf. Will only have about half of its present mass because the helium shell flashes. And the stellar wind, when it was a red giant and an AGB star, it will eventually shed about half its mass, and the final remnant will only be about half the mass of the sun, about 0.45 mass of the sun, something like that. Anyway, So this was a more massive star when it started out. 1.053 solar masses. Its radius, based on, you look at its temperature, you look at its surface temperature and its luminosity, and you use that to calculate what its radius must be from L equals 4 pi r squared sigma Tef to the fourth. Its radius works out to be 5.5 times 10 to the, I have fifth kilometers in my notes and that can't possibly be right. It must be 5.5 times 10 to the third kilometers, because that's the only thing that makes sense here, for its radius. So, you know, kind of Earth-sized-ish is what we're talking about here. If we put those numbers in, if you calculate what the density is by taking the mass divided by 4/3 pi r cubed, et cetera, put those numbers in to that expression we just had for V at the Fermi surface, we get V is equal to 3.4 times 10 to the 8th meters per second. Does anybody see a problem with our calculation yielding V being 3.4 times 10 to the 8th meters per second? Yes.
Speed of light is 3 times 10.
This is 3.0 times 10 to the 8th meters per second, right? This is greater than C. So that can't be right. It must be assuming 1/2 mv squared was the kinetic energy was wrong, that this is actually a relativistic. So if we correct it and use the relativistic formula for the kinetic energy, we would get a speed that's less than the speed of light. But the fact that we use the Newtonian expression and got a speed greater than the speed of light says, oh, we must be in the relativistic regime where 1/2 mv squared is no longer an accurate expression for the kinetic energy. So our electrons at the Fermi energy must be relativistic. And so let's look at what the consequences are of that. How does this change things? So far, what questions do you have? Questions, comments, observations? I'm always hoping somebody will make a comment or an observation, and it never, yes. Make a comment, please, or you can have a question too, that's fine too.
I have a question.
Okay, we'll go with that.
So if the speed we calculated was less than the speed of light, we would not be worried if it's...
Well, it depends on how close we're talking. If we got that the speed was 90% the speed of light, we'd still be worried. We would say, probably we should be using the relativistic formula. If the speed is any substantial fraction of the speed of light, that would be telling us 1/2 mv squared wasn't a good approximation in that case to the actual expression for the kinetic energy. And we'd have to use the correct expression in relativity for the kinetic energy. And of course, it's always correct to use the relativistic expression, but it wouldn't matter if this had been much less than the speed of light. If we corrected it for relativity, it would hardly make a difference. But here it would. If we used the correct formula, we would have got something that was close to, but still not equal to the speed of light.
What's the cutoff or threshold?
There isn't a strict threshold, right? In other words, things don't suddenly become relativistic. It's not like, well, at 2 times 10 to the 8th meters per second, it's not relativistic. All of a sudden, after that, it's relativistic. No, things kind of, fade into being relativistic, and it's up to you to decide how much toleration you have for the corrections. So, I mean, in general, the relativistic formula is always right. It's just that it's harder to use, a little bit harder to use. So if you can get away with that, we often do, is what it comes down to. Yep. Alrighty, so So let's consider the extreme relativistic case where not just electrons near the Fermi surface, but essentially all the electrons are relativistic. Let's consider the extreme relativistic case where all the electrons are relativistic. Let's take this to the extreme. We're just going to assume all of them are. Now typically, okay, the lowest energy ones might not be, but let's just keep it simple and assume they're all relativistic. So what's the expression for, well, what's the general expression, right? E squared in relativity is equal to what? Do you remember? E squared is equal to, so that's a big part of it, okay? So I'm going to put plus p squared c squared. And then what's the term here? MC squared. Squared, right? Right, so in general, E squared is MC squared squared plus p squared c squared. Simplifies to E is approximately just PC in the extreme relativistic case, because as the momentum gets larger and larger, eventually PC becomes much bigger than MC squared. And that's the extreme relativistic case. If PC, if that contribution to the energy is much bigger than MC squared, what do we call particles MC squared? That is its rest energy. That's its rest energy. So if this contribution from the momentum is much bigger than the rest energy, we're in the extreme relativistic limit, and we could toss that term, and then E squared is p squared c squared, or in other words, E is approximately PC. Can you name some particles for which E is exactly PC? Why? Some particles that are fully relativistic, they're going the speed of light?
Photons.
Photons, yeah, photons. What's the mass of a photon? It ain't none, yeah, there's no mass in that case. For a photon, it's always just E squared is p squared c squared, E is PC. And for any particle, if you're going fast enough, you get closer and closer to having the same expression as a photon. E is equal to PC, with a small correction for the rest energy. Oh, but we're doing quantum here. We want to think quantum mechanically, and it still works the same way. P and K are related the same way, relativistically or non-relativistically. The relation between momentum and the wave number K is P is equal to, you did it last, no, that's lambda. So lambda is 2 pi over K. Then from that we developed P is K, 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 yes. H bar. Yes, P is H bar K. P is H bar K. So the energy is H bar Kc for our extreme relativistic electrons. As opposed to, remember, when they're non-relativistic, we just said the kinetic energy is p squared over 2m, and then we said, okay, well, that was h bar squared k squared over 2m. So notice this big difference. Now E is proportional to k instead of proportional to k squared in this limit, and that's going to make a big difference here. So I want to emphasize this E that I just wrote there is for each particle. Now I'm going to switch to E, meaning the energy of the whole gas, added up over all the electrons. Then the total energy of our degenerate gas is, we're going to write the same integral as before, but with our new expression for the energy as opposed to of the individual particles, as opposed to the h bar squared over 2m, h bar squared k squared over 2m, we're going to use h bar kc instead. So E total now here, right, this was just for one particle, now I'm adding it up for all the particles. So maybe I should have said here for one electron or something like that. But in any case, it's going to be, all right, I'm going to integrate over K space. So we've still got our octant of the Fermi sphere. So here's my Kx, Ky, Kz axis. What do I call the radius of the Fermi sphere inside which, in the ground state, all the states are occupied? Why, this is K sub f, right? The Fermi radius, right? And what we're going to do is, just like we did before, we're going to look at thin shells. We're going to look at thin shells. So each shell has radius K. And what are we going to call the thickness of the shell? dk, yep. And so the energy will be an integral from K equals what to what? 0 to K Fermi, right? We're going to add up all inside the Fermi sphere, really the Fermi octant, if you like. The integral of 0 to K Fermi. And now we'll have h bar kc times v over pi cubed times 2 times 1/8 times 4 pi k squared dk. And you're going to tell me why each of those terms is there. So what is 4 pi k squared dk? That's the volume of the shell. That's the volume of this shell of thickness dk. It's really the K space volume, right, which has units of reciprocal meters cubed. K space volume of shell of radius K, thickness dk. So it's the thickness of our, it's the volume of our little thin shell in K space. When we include volume of spherical shell, I'll put the whole thing, of a spherical shell of radius K, thickness dk, but then I multiply by 1/8 because only the first octant, right? Only first octant. We're living in the first octant of K space because that's where all the cool wave vectors live, and that's where we want to be too. All right? And then 2 is there because of spin, right? Because of spin. And V over pi cubed, the volume of the container over pi cubed, why, that's the density of states, number of states per unit K space volume. Number of states per unit K space volume. So if I take 1/4 pi k squared k dk, that's the amount of k space volume. I multiply by the density of states, number of states per unit k space volume, and then I multiply that by 2 because every one of those states has 2 electrons in it. Put all this stuff together, all this stuff combined, how could you describe that in words? All those terms represent the number of what, where? The number of electrons whose states are in that spherical shell, spherical octant of a shell, if you will. So, number of electrons with k values, really the vectors, k values inside the shell. That's how many electrons whose k values, kx, ky, kz, whose wave vectors are inside the shell. If I drew the wave vector of the electron, it would be sitting inside that shell corresponding to its k sub x, k sub y, and k sub z values. So that's the number of electrons inside the shell. And h bar kc is, that's how much energy each of those electrons has. That's the energy of an electron in the shell. So, number of electrons in the shell times how much energy each one has is the total amount of energy of those electrons in the shell added up. And then the integral says, now add that up for all the shells to get the total energy of all the particles in the star. Yay! Questions, comments, observations? Anybody not happy? I want every, yes?
I just want to clarify that
Yeah.
because we're taking it as relativistic and we're not including the mass c-squared?
Correct. We're ignoring that piece. So strictly speaking, yes, strictly speaking, this should be the square root of mc squared squared plus h bar squared k squared c squared. It should be that, but we're in the extreme relativistic limit where we can ignore that term. So this is an approximation that gets better and better the more extremely relativistic our electrons become, is what it comes down to. Yes, another question.
Where does the b over pi cubed?
It comes from, you were in Cleveland. Yes. If you haven't watched those videos yet, are you in for a treat where you will learn about why that is the number of states per unit volume of K space that describes the wave functions of our electrons inside of our cubical box. Yes, so therein lies a story. Please enjoy that story. Please come talk to me about that story should you find the need to. Yes, okay. What other questions does anybody have? Shall we do the integral? Why, yes, we shall. So it's another easy one to do because you got a bunch of constants that we can factor out times a really easy integral. So this is equal to h bar c times the volume of the box divided by pi squared, right? Because you got pi over pi cubed is 1 over pi squared, and you've got h bar times the volume of the box times the speed of light, and then we've got k times k squared is k cubed. So integral from 0 to k Fermi of k cubed dk. I would argue that we can probably do that without Mathematica. And if you want to argue with me about that, just leave, just go. I'm going to go tell Dr. Nunemacher on you if you, don't do that, right? Yeah. So notice, before this was k to the 4th power, because it was h bar squared k squared over 2m. That's the only difference. Before this was h bar squared k squared over 2m, and so you had a k squared times a k squared is k to the 4th power. Now it's k to the 3rd power. Quick! Evaluate that integral. What do you get? K Fermi to the 4th over 4, because you're going to subtract 0 for the lower limit. So this is h bar c, volume of the box, over pi squared, times 1/4 K Fermi to the 4th power. Now, the expression for K Fermi in terms of the number density and all that, it's the same as before, because in terms of occupying K space and all that business, you're still occupying a grid in K space. The wave functions, even relativistically, they still look the same. It's just that they have different energies as before. So we still get to use the same expression for K Fermi that we had before. And so this becomes h bar c, volume of the box over pi squared, and then 1/4. And then when we find K Fermi to the 4th power, well, remember that K Fermi was 3 pi squared times the number density to the 1/3 power. So when I raise that to the 4th power, I get that to the 4/3 power. So before, this became 3 pi squared n to the 5/3, because this was an integral of k to the 4th. Now, because it's an integral of k cubed, it becomes 3 pi squared times the number density, number of particles divided by the volume of the box, to the 4/3 power. That's kind of the upshot here. So we're going to want to differentiate this in order to find the pressure. So, and we're going to so let's see, we differentiate the energy with respect to what to find the pressure? The pressure was minus dEd. Do you remember? Where you could page back in your notes a page or 2 or 3 or whatever. It's dEd. The pressure is dV. Yeah, we're going to differentiate with respect to volume to get the pressure. So let's put this in terms of volume so we can actually take that derivative. So this will be 3 to the 4/3 times pi to the 2/3 divided by 4 times h bar c times the number of particles in the number of electrons in our box, n to the 4/3 volume to the, well, I'm not going to make this mistake again, volume to the minus 1/3. And that's because little n is equal to who over who else?
V over N.
What's that?
V over N.
Stand on your head and say it again. N over V is number of particles per unit volume. N over V. Little n is the number of particles per cubic meter. So that's the total number of particles divided by the volume of the box, because we're assuming it's constant. Won't be true on our real star. Shut up. We get the same result in the end, even if you're more careful about that. Okay, so I've got a V here, and I'm dividing by V to the 4/3. So I've got, in other words, V to the 3/3 over V to the 4/3, which is V to the minus 1/3, is how this V right here arises. Are you happy with that? Why, that's V to the minus 1/3, because I'm dividing V by V to the 4/3. And then I just took the 3 pi squared out, and 3 pi squared to the 4/3 is going to be 3 to the 4/3, and then pi to the 8/3. Oh, but when I'm dividing by pi to the 6/3 down here, turning that into pi to the 2/3. Okay. Is everybody on board here? Still on the train? Can I keep the train going down the track here? All right, let's keep that train going down the track. So 2, 4, 6, 8, we want the pressure, so now we differentiate, yep, right? So P is minus dE dV, minus dE dV, okay? So that'll be all the junk out front, 3 to the 4/3 pi to the 2/3 over 4 times h bar c times n. What is the derivative of v to the minus 1/3 with respect to v? Yeah, minus 1/3 v to the minus 4/3, right? So times times, but it's a minus right here. So I'll have a minus minus, which will take care of that and make it a plus. So I'm going to times 1/3. Oh, and this, sorry. I didn't mean to just say n here. I meant to say n to the 4/3, right? Still n to the 4/3. And then this v became to the minus 4/3. But n to the 4/3, v to the minus 4/3, why, that's the same thing as n over v to the 4/3, right? Which is the same as, why, what might I want to replace n over v with now? Little n. So this is little n to the 4/3. So again, the pressure only depended on the number density in the end. It didn't depend separately on the volume and number of particles. It depends on the number density question.
Should there be a minus sign on the front?
So there would be if I put a minus sign right there and I put a minus sign right there because of taking that derivative, right? The derivative of v to the minus 1/3 is minus 1/3 v to the minus 4/3. So if you like, you can keep this minus sign and keep this minus sign, but then they just get rid of one another, right? Minus minus is plus. So I just didn't bother. I just didn't put it there.
How did we get the one over there?
Which one right here? This one?
No, when you were not that term, that term.
This right here? Oh, it's because, in other words, if I were to just, I'm taking this derivative. Well, there's a minus sign to begin with. I'm taking this derivative, la, 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 la. Okay, I'm taking the derivative of v to the minus 1/3. Why, that's minus 1/3 v to the minus 4/3. Okay, and then I would say, oh, minus minus is plus. So mentally, I was just like, I knew minus minus was going to be a plus, and I didn't bother to write either minus sign, but I could. Yeah. Okay. And so we get that this is, we can do some grouping here, 3 pi squared to the 1/3 power over 4 h bar c, cute little n, the number density, to the 4/3 power. That's the pressure. And then we do what we did before and rewrite the number density in terms of Z and A and rho and MH, just like we did before, because usually we're more attuned to figuring out the mass density of our white dwarf because we can take its mass divided by its volume. And when when you do a fun problem in the homework where you're finding the mass of a white dwarf from the orbital dynamics of its companion, you're just going to find its mass. You're not going to find its number density directly from that. So let's put the number density back in terms of ZA, rho, and MH. And what we get is that the pressure then is 3 pi squared to the 1/3 power over 4 times h bar times c times the quantity Say it with me, Z over A. No, Z over A times rho over MH, right? We argued last time that little n was Z over A times rho over MH, all to the 4/3 power. And here's where we put the box around it and tie a nice bow and all that sort of thing. Because, in other words, P is some constant, right? All of this other stuff is just constants times rho to the power of 4/3. Whereas in the non-relativistic case, we found P equals, it's another constant, it's not the same constant, but it's a constant. Another constant times rho to what power was it last time? It was 5/3 last time. It was 5/3 last time. It was 5/3, but now it's 4/3. For the relativistic case, the extreme relativistic case, it's 4/3. So now let's see, the power of rho that the pressure depends on, why that's the, can you remember the index? What's my bird going to be taught to say? Polly wants a tropic. It's the polytropic index. It's the polytropic index. Right? See how stupid things like that can help you remember words and names and stuff like that, right? I'm all into mnemonics. I got a bird going, Polly wants a tropic, which is ridiculous, but it helps me remember, oh, it's polytropic, you know, right? So now the polytropic index, our bird is on a cage on a beach with palm trees and it's a lovely tropical scene, right? So, or our bird is in a house and there's a balloon bubble of its dream of tropical beaches and stuff like that. That's why our bird is going, Polly wants a tropic, right? Okay. So now the polytropic index is 4/3 instead of 5/3, which, cool, what's that mean? It means it becomes unstable, as we will show by doing what we call a perturbation analysis. Some of you might have done projects that involve like perturbation-y kind of things, even if I don't know if you called it that, but let's do a perturbation analysis, shall we? And then you guys will all be so smart because the first time I saw perturbation analysis, I was in grad school, but now you're seeing it as undergrads, so there you go, right? Life is good. Because I know my life is better when I get to do some perturbation analysis. It's not at all perturbing. It's delightful. All right? So, but first we'll take a break because it's almost that time. So therefore, drive to Cleveland in every possible emergency. I get it now. It makes so much sense. Yes, perfectly logical. Well, I'm bleeding out, but I better still get to Cleveland. Here, hold my arm, would you?
I'll tie you.
Yeah. Yeah. Yes. 80, well, which college are you talking about? Well, I went to Case Western Reserve for undergrad. Yes, and I graduated in a year, yes. In a year. It was a year, correct. It was a calendar year in which I graduated. That is correct. Very good. So, all right then. All right. So, we're going to do example, wrong chapter, 14.1. Oh, the chapter about pulsating stars and so forth. Yes, because it's relevant here. So, pulsating stars are ones where instead of a kind of a more permanent long-term equilibrium between pressure and gravity, sometimes pressure is winning and sometimes gravity is winning, such that they oscillate, such that they go back and forth trading who's winning, and they vibrate, so to speak. They pulsate in and out. And so in chapter 14, they talk about that. Not coincidentally, Carolyn Osley's research specialization is pulsating stars. And so, of course, they had to write a chapter about that. It's a really nice chapter. We don't have time to cover it, but we're going to use this piece of it right now. I did 1 year cover it, and I can send you the videos if you want to see them. Yeah. So, all right. So we're going to make a simplified model of our white dwarf, where we have just one shell of mass m, just think of one shell of mass m, and this would apply. This can apply. It's a rough model for pulsations of any star, not just a white dwarf, and we're going to say that really the whole mass of the star is sitting at the center, because remember that when it comes to gravity, if you have a spherically symmetric distribution of mass, it behaves as though all the mass were at the center. And if you're inside of a star, remember, all that matters is the mass interior to your radius. So we're going to say, okay, well, here's like the surface of the white dwarf, and we're going to look at a shell at the surface, and gravitationally speaking, it feels the full gravity of the white dwarf as though all the mass m of the white dwarf were sitting there at the center. And meanwhile, we've got miracle massless gas. So we just assume there's this massless gas inside the shell whose only job is to exert pressure on it and not to contribute any gravity. And this is just to keep it simple. It's much more complicated if you have mass versus radius and details. You'd have to look at every shell, This is a back of the envelope calculation that gives us the answer that we're looking for. It's one of those. It's very common to do such things. And so we'll say that the radius of our white dwarf is capital R, that we're looking at a shell on the surface, how it responds to this massless gas that's exerting pressure on it to keep it from collapsing towards the center. So that's the picture. What questions do you have at this point about the picture here of what's going on? So let's see what happens. All right, Newton's second law. Newton's second law says what?
Force is mass times acceleration.
Yeah, mass times acceleration equals force. Was it true? So, and I've been doing this more and more these days. When I say Newton's second law, I prefer to say A is F over M, because force is the cause and acceleration is the response. And so I know Dr. Trees these days, I noticed this when I was teaching lab last semester, they always started with A equals F over M instead of F equals MA. Did he have you guys do that too? Like it's A is F over M. Or did he let you say F equals MA? Oh my God, he let you say F is M, which is, I mean, it's mathematically equivalent. But I think there's this thing in pedagogy and physics now to emphasize, because students often get confused and they think MA is a force. Like if they're writing a free body diagram and they say, well, here's the MA force. And no. MA, right, is the response to a force. It's not a force itself. And so But okay, since your brains were already poisoned by writing F equals ma, I'll do that here. So the mass of the shell times d squared r dt squared. So really, I should take like a little dm of the shell, but it's all moving in the same, right? We're assuming that it all contracts radially and expands radially, so it's all moving towards the center. So we can pretend, even though it's a little sloppy, because really you should look at one little chunk of it, it's actually moving in a definite direction in space. We can just say md squared r dt squared, mass times acceleration, is equal to, what's the gravitational force on that shell of mass m? So it's all a distance capital R from big M here, and Newton's law of gravity says that the gravitational force is g times what over what all goes in there. Yeah, g m1 m2 over r squared, which in this case becomes minus g big M little m over r squared, and the minus is there because it's a force towards the origin, towards zero. It's trying to make r decrease, if you will. So md squared r dt squared is minus gmm over r squared. So there's an inwards gravitational force on our shell. Let's say our miracle massless gas has pressure P. What's the other force on that shell? It's a pressure force, right? Is that pressure force going to be inwards or outwards? Outwards, so it's going to come in with a plus sign. And what will the net force be? In terms of pressure, force is pressure times area, right? Because pressure is force per unit area. So pressure times area is force. What is the area of the shell? So the lower surface of the shell, radius r, has what area? Like any self-respecting sphere, and even ones that have no self-respect, 4 pi r squared, right? So 4 pi r squared times the pressure. That's Newton's second law. Again, we're being a little sloppy because really you should look at a little dm and all that. But if you integrate it, you would just get exactly that. You can pretend that it's like linear motion. Yes? It absolutely should, and thank you for pointing that out. I was just testing you to see if you would notice. And I have a bridge I would like you to buy in Brooklyn. Yes. Okay, yeah, thank you. Yes, 4 pi r squared p, absolutely. Okay? So that's the equation of motion. So you might have P winning, in which case there will be outward acceleration, or you might have the gravitational force winning, in which case there will be inwards acceleration. But if it's in equilibrium, and when you do perturbation analysis, that's what you're generally doing. You are, quote unquote, perturbing around the equilibrium configuration. You're saying, what if I started with equilibrium and made a small change? Like I made the radius a little bit bigger than the equilibrium radius and I let go. What would it do? Similarly, if you have a mass on a spring, then like, well, we got a mass on a spring and it's hanging, right? Equilibrium would be when the downward gravitational force, you've stretched the spring just enough so that the upward spring force is equal to the downwards gravitational force, and then you could perturb it. You stretch it a little bit. What will it do as a result? It'll go wangy, 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 because it'll keep overshooting the equilibrium both directions. And yeah, it goes wangy, wangy, wangy. That's the technical term, also called harmonic motion, right? Yeah, wangy, wangy, wangy. So we're going to do that here. What we're going to do is we're going to imagine we change the radius a little bit, and the question is, does it go wangy, 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 or does it go whoosh, or whoosh? And what we'll find is that when the polytropic index is 5/3, it'll go wangy, wangy, wangy. But when it's 4/3, well, it'll actually be like a styrofoam ball where if you pushed inwards, it just keeps its shape. And then we'll say, oh, but GR comes in and makes it go instead of going winky, 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 or instead of just changing to a new radius that's also still stable. That's the big picture of what we're doing here. So in equilibrium, what's the acceleration if it's in equilibrium, just keeping a constant radius? 0, right? And so that says that the right-hand side has to be 0, and that says that GMM over R naught squared. So R naught will be the equilibrium radius, the radius where it would be in equilibrium, is equal to 4 pi R naught squared P naught. So there'll be some equilibrium pressure, equilibrium radius. So 0 subscript denotes equilibrium value. Denotes equilibrium value. And here's where I'm going to do something that might be new for you. This might be something you've never seen before. So just sit here thinking about how much of a genius you are learning this right now as a junior or a senior when your professor never saw this until he was in graduate school, right? So let's perturb the equilibrium. This is a very common technique when we're doing what's called stability analysis, trying to determine if our system is stable or unstable. Perturbation. Let R go to R naught plus delta R, where delta R is a small change. Actually, I'll just say R equals R naught plus delta R. You can think of it as, but in other words, the idea is we start within an equilibrium and then we increase it by just a little bit. So our new radius is the equilibrium value plus a little bit extra. Or maybe the other way. We either, if delta R is negative, we squished it a little bit. If delta R is positive, we expanded it a little bit. So delta R is positive and I expanded a little bit. What happened to the gravitational force on the shell? Did it get bigger or smaller? Got smaller because R got bigger, so it got further from the center. So that would drop the gravitational force a little bit. And then the question is, okay, what happens to the pressure force when I make that same expansion? And then the question becomes, after you do that, is there a restoring force back towards where you started, or is there a force outwards away from where you started? And that makes all the difference. Does the system, when I perturb it, tend to want to go back towards equilibrium or get further and further away from equilibrium? That's what we're looking for here. Okay? We will also assume that P now becomes P naught plus delta P. And for now, we won't specify any relation between delta R and delta P, but then we'll use the fact that the gas we'll assume is a polytrope, and that will give us a relation between delta P and delta R that will allow us to say things, basically. So what questions do you have so far? And again, this could be new, so you might be like, what? But that's okay. That's how these things happen. So I plug those new values for R and P into my equation. So this turns it into m d squared of R naught plus delta R dt squared is equal to minus G big M little m over R naught plus delta R squared plus 4 pi times R naught plus delta R squared times P naught plus delta P. And you at first might think, oh, and then I'm going to expand all those squares and go from there, and you would be wrong. Because what we're going to do is a linear stability analysis. We're only going to, as we say, keep terms up to linear order in delta R and delta P. In other words, we're going to do this deal where we use 1 plus x to the power of n is what? As an approximation, right? For x much, much less than 1, 1 plus x to the n is approximately, do you remember?
1 over that thing squared.
No, it's, what is it? No, it's
1 over x.
Huh? 1 plus nx. Remember that? 1 plus nx, right? You may not have realized it at the time, but when you saw that for the first time, you made a friend for life. And now your friend is coming back to hang out with you. I know, yes, right? I mean, the simplest example is 1 plus x squared is 1 plus 2x plus x squared. If x is much, much smaller than 1, then x squared is much, much smaller, 1 plus x the quantity squared, yes. 1 plus x the quantity squared is, gosh dang, is equal to 1 plus 2x plus x squared, right? If x is a lot smaller than 1, then x squared is a lot smaller than 2x, right? If x was 0.001, x squared is 1/1,000,000th, right? 0.0000, however many, 1, right? 10 to the minus 3 squared is 10 to the minus 6. And 2x is 0.002, right? Well, 1/2000th is a lot bigger than 1/1,000,000th. And so you can throw away this term in the limit that x is very much less than 1 and just replace it with 1/2x. This is just saying, yeah, it turns out for any power n, I can do that same approximation if x is very, very small. That's right, that's where that's coming from. Okay. Of course, your favorite way to think of it is it's the first two terms in the Taylor series expansion for 1 plus x to the n. I know how much you love that, right? Either way, we're going to use that here. We're going to use that here. We're going to use that here. And then we're going to multiply things together and throw away terms that are small compared to everything else. It's always the trick here. So, from our friend for life, one plus x to the n is approximately 1 plus nx for x much, much less than 1. Right? From our friend for life. What's that?
Never have I ever seen a professor draw that.
Well, now you have. Okay? So, have you seen a professor blow a kiss to a math relation? Love it so much. We have that 1 over r naught plus delta r squared, right? Look at the tricks we can do here. Well, that is 1 over r naught squared times 1 over 1 plus delta r over r naught squared. So I factor out R naught squared, right? Because I could just put this back through and it would turn into R naught plus delta R, the quantity squared. So I factor out R naught squared. Oh, but now that means I can write this as 1 over R naught squared times 1 plus delta R over R naught to what power? In other words, I just moved it up into the numerator, so instead of 1 over 1 plus delta R over R naught squared, it's just 1 plus delta R over R naught to the minus 2, and we're assuming the perturbation is small, right? We're assuming that delta R over R naught is much, much less than 1. We're assuming a small perturbation, meaning the change is small compared to the original value. That's the limit we're making here, is that changes are small compared to what we started with. So is this of the form BFF forever, right? BFF, well, best friends forever? 1 plus x to the n, where x is much smaller than 1? It is! Delta R over R naught is much smaller than 1, and it's raised to minus 2. That's our n in this case. So we can say that this is approximately 1 over R naught times, squared, because it's factored out 1 over R naught squared, times 1, and then what else am I putting inside the parentheses? 1, 2 delta R over R naught, right? 1 minus 2 delta R over R naught, right? Because delta R over R naught is playing the role of x, and minus 2 is playing the role of n, so 1 plus nx is 1 minus 2 delta R over R naught. And similarly, with this piece, if we liked, we could do the same kind of thing and use 1 plus nx and all that kind of stuff. Or we can just expand it out. So I'll just do it that way for that. You'll get the same result anyway. If we look at the term R naught plus delta R squared times P naught plus delta P. Okay, what's R naught plus delta R squared? Well, that's going to be R naught squared plus delta R squared plus what else? This piece right here, I'm done by R naught plus delta R squared. By itself, I get R naught squared plus delta R squared plus, let's FOIL it, 2R naught delta R, right? Plus 2R naught delta R. That's the first piece. Maybe I'll put square brackets around it. Times P naught plus delta P. And now what I do, I could expand this whole freaking thing out. But what I do is I say that I'm only going to keep terms linear in delta R and delta P, or terms that don't have them in there at all. Because if delta R and delta P are small, then delta R squared is a lot smaller than delta R is. Delta R delta P is a lot smaller than delta R or delta P is, so to speak, when you, I mean, a little sloppy with units here, but in any case, I'm going to say keeping only terms linear or lower order in delta R and delta P, gives that we'll just have, well, what will we have? We'll have R naught squared P naught from these two terms multiplied together. R naught squared times delta P, is that linear in delta R and or delta P? Linear means delta R and delta P only appear to the first power or the 0th power. Wait, so R naught squared times delta P, is that linear in delta R and delta P? Or, either one, it could, sorry, right? Does that have any power of delta R or delta P in it higher than the first power? Or a product of them? It doesn't, right? It doesn't. So you get plus R naught squared delta P. I keep a term like that. I'm keeping terms that have delta R or delta P to the first power and no cross products of delta R and delta P with one another. The idea being that for small delta R and delta P, terms to the first power will be much larger than terms to the second power of those terms. And so I'm seeing some blank stares, and so is that making sense or not? Yes?
Are we talking only in terms of delta P and delta R, not like...
Not R naught squared, no, because those are big things. Those are big things, and we want to keep those. What we're trying to do is throw away small terms in the end. So in other words, the exact expression over here would be, I would do the full multiplication. But then I'm going to say, yeah, but the terms that have delta R times delta P, or delta R the quantity squared, or delta P the quantity squared, those will be a lot smaller than the other terms because they involve products of small quantities. And a product of two small numbers is a lot smaller than either one of the small numbers by itself. So I keep a term like R naught squared delta P. Now, if I go through here, I'll have delta R squared times P naught. Do I keep that term? No, because it's got delta R squared in it, and delta R squared is a lot smaller than delta R. Again, I'm being a little sloppy here, and I should really be doing ratios, but in any case, it's going to be true that P naught times delta R squared we'll expect to be a lot smaller than something like R naught squared times delta P, because this has one power of a small number in it, and delta R squared has two powers of a small number in it. So I don't use P naught delta R squared. So I'll put it there. So I say plus P naught delta R squared. I neglect terms that have more than one power of delta R and or delta P in them. So I throw that one out. I'm going to toss it. Then there's going to be a delta R squared delta P. Am I going to keep that term? Oh, emphatically not. That's 3 powers overall there. So that's like, oh, no way, go away. We're not going to think about keeping you in this party. Plus 2 R naught P naught delta R. Am I going to keep that term? Yep, I would keep that term. Plus 2 R naught delta R delta P when I multiply those together. Am I going to keep this term? I am not, because it's got a product of two small quantities in it. So I'm going to throw that away. The idea here is that these 3 terms are much larger than these 3 terms are because of them not having products of small quantities in them. It's kind of like saying if I had 1 plus x times 1 plus y, the exact result is 1 plus 2 at 1 plus, what is it? 1 plus x plus y plus xy, right? That's the That's when I multiply that out, right? 1 plus x plus y plus xy, right? And if x is 0.001, and y is 0.001, right? Then this becomes 1 plus 0.001 plus 0.001 plus what's x times y? 0. Yeah, 1, 2, 3, 4, 5, 1. Okay. Which term should I not keep? This one, the xy term. We throw away products of small quantities because they'll be much smaller than terms that don't have products of small quantities in them. That's the logic here. The terms that have products of small quantities, delta r times delta p, or delta r times itself, or delta p times itself, are much smaller than everyone else, and so they don't get to stay in the party. They have to go home. And we only keep the other terms. That's the big picture here. Okay? Questions, comments, observations? Okay, well, we'll have to bring this one into the party too and only keep the linear order and below terms. And so I'll let you complete this on your own to get the following result. Expanding the equation of motion and keeping and retaining only terms linear in delta r and delta p, linear in delta r and delta p, or free of them, not having them in them, yields please joyfully show that to yourself later. But we've done most of it just by doing that. Yields the following. That m d squared delta r dt squared is equal to minus g m little m over r naught squared plus 2g big M little m over r naught cubed times delta r plus 4 pi r naught squared p naught plus 8 pi r naught p naught delta r plus 4 pi r naught squared delta p. That's what you get when you expand everything out and only keep terms that are of linear order in delta r and delta p or don't contain them at all. No terms that are delta r times itself or delta p times itself or delta r times delta p, or even worse, delta r squared times delta p. None of those things get to stay in the party because they're tiny and we hate tiny terms. So we toss them. Yes?
Are we only doing delta r? Like these
Gosh, that's a great question. So what is m d squared r naught dt squared? It's 0 because what is R naught? A constant. It's just the constant equilibrium radius. So 0, since R naught is just a number. It's a constant, right? It's the equilibrium radius. It can't change. It's the equilibrium radius. So we don't need that piece right there. And so that's why it's d squared delta RdT squared. Because what we want to know is, this is telling us how does the change in the radius change on time, basically. All the variation in the radius is contained in delta R there. And I'm going to do this. Why could I do that?
Because R non-equilibrium.
So what was our equilibrium condition in the first place? It was that GMM over R naught squared was 4 pi R naught squared P naught. That was equilibrium, right? In equilibrium, we have that GMM over R naught squared was equal to 4 pi R naught squared P naught. That was the equilibrium condition in the first place, that the gravitational force on the shell was equal to the pressure force on the shell. So this is the equilibrium condition. So these two terms cancel one another. These terms cancel each other. So it's not that they're 0, it's that they're equal and opposite to one another, because pressure equals gravity in equilibrium. Okay? And so that means that our equation is this equals the sum of these three other terms. Okay, so now, questions? Because now we're going to make use of the gas being a polytrope. Because we can't go anywhere if there's no particular relation between delta R and delta P. The only thing we can say anything substantial is if delta R and delta P are somehow linked to one another. And they are. So now assume that the gas inside the shell obeys a polytropic gas law. And one way to say it was P is something constant rho to the gamma. Another way to put it that we've used before when we did our convection analysis was P volume to the gamma is equal to a constant. So for a polytrope with gamma being the polytropic index, PV to the gamma is a constant. Or another way to put it is that the pressure times the radius to the 3 gamma is equal to a constant. Why, if PV to the gamma is a constant, is it also true that PR to the 3 gamma is a constant? So here our gas has some radius r. Here's the relation between its pressure and the radius of the star. This is where we're saying something definite. This is how we will relate a change in pressure to a change in radius, because the pressure times the star's radius to the 3 gamma is a constant. Why, if PV to the gamma is a constant, is it also true that P radius to the 3 gamma is a constant?
Maybe we're treating it as a square, then when
No, we're treating, strangely enough, we're treating our star as a sphere. Yes?
Use just some constant times r cubed. And
Right.
just move that over.
That's exactly right, yes, because PV to the gamma is constant is the same thing as P times 4/3 pi r cubed to the gamma is a constant, right? Because the volume is 4/3 pi r cubed, and so P r to the 3 gamma is constant over 4/3 pi to the gamma, which just call that the constant again, right? So in other words, okay, this is a different constant, strictly speaking, than this one, because to get this one, I have to take this one and divide by 4/3 pi to the gamma, but, you know, who cares? The point is this, it's a constant. Okay, so pay attention, pay attention. We are now going to relate delta R and delta P using the fact that P r to the 3 gamma is a constant. So I find the easiest way to do it is then say, okay, take 2, 4, 6, 8 time 2 natural logarithmiate, so to speak. Let's take natural logs. That was strained but effective, I think. Then take natural logs of both sides. What's the natural logarithm of P r to the 3 gamma? So, well, it's not the whole thing to the 3 gamma. So the logarithm of A times B is logarithm of A plus logarithm of B, right? And the logarithm of x to the y is y log x. So we'll use that combination of facts here. The logarithm of P r to the 3 gamma is the natural logarithm of r plus the natural logarithm of P plus the natural logarithm of r to the 3 gamma, but that's 3 gamma log P. So I can say log P plus 3 gamma log r is what I meant to say there. I'm tired. Okay, so log P plus 3 gamma log r equals log constant, but every time I make a new constant, I'm just going to keep renaming it constant, right? Because the point is not what the constant is equal to. The point is that it is a constant. So log P plus 3 gamma log r is a constant. Take differentials. But write delta P instead of dP. In other words, in math class, or in physics class, because we're sloppier than the mathematicians, we say dP is a little change in P, dr is a little change in R. But we're calling little changes deltas, so we're going to keep calling them that here. In other words, we're going to think of delta P instead of dP when taking differentials. So what is, back to math class, what is d of log P? What do you do? What's the differential of log P in terms of the differential of P? It's dP over P, right? It's dP over P, because the derivative of log P is 1 over P, right? So when I take differentials, I still have to have a dP there, right? Put another way, the derivative, if I wanted to take derivative with some variable, d log P dx would be 1 over P dP dx. And now, in what is bad algebra but good calculus, multiply through by dx and just get d log P is dP over P. A small change in the logarithm of P is the change in P divided by P itself. Are you okay with that? That's the idea here. And so, but I'm calling everything deltas instead of d's. So when I take differentials, I get, nah, I'm running out of chalk. Ugh. You know what I think about, like running out of chalk. You know how much I love short chalk. Anyway, delta P over P is the differential of log P. What's the differential of log R?
dr over r.
Yeah, same thing. Delta R over R is just we change the name of the variable, right? So I get plus 3 gamma delta R over R. And what's the differential of a constant? It's 0 because constants can't change. So PR to the 3 gamma equals constant implies a small change in pressure divided by the pressure plus 3 gamma times a small change in radius divided by the radius adds up to 0 in the limit. It's usual in the limit as delta R and delta P go to 0. It's that limit where it becomes exact, but we're considering small changes. So we are in the limit where we can get away with this. So this says that delta P over P naught, because P naught is what we're calling the original value of P that we're slightly changing, is equal to minus 3 gamma times delta R over R naught. And the point here, and I know that, right, have any of you seen something like this before? I suspect the answer is you've never done anything like this. So I realize, right, there's that like barrier is that this is the first time you're seeing it, but cool, it's the first time you're seeing it, so you're developing a new way of thinking about things. The point here is that because the gas is a polytrope, so that its pressure times so that the pressure of the gas times the radius of the star to the 3 gamma is constant, and gamma is the polytropic index. So for the non-relativistic white dwarf, we're going to make that 5/3, and for the relativistic one, we're going to make it 4/3, and that's going to end up making all the difference. We have a relation between if I change the radius of the star, this is how much the pressure changes by. That's the point. That the gas is a polytrope gives us a way to say, if I make a given change in the radius, I now also know what the change is in the pressure, and so I can put those into that equation and see what happens. Glorious. Right? Glorious. Play along with me here. Glorious. Glorious. Yes. Glorious. That's right. Yes. Fireworks. Fireworks. Okay. Wow. Okay. So, yeah, I don't like what time it is, because we're going to have spring break, and then we're going to come back to this, and you're going to be like, what? I mean, you already might be kind of like, huh? But after spring break, you're going to be like, huh, what? Or something like that. But still, well, that's kind of where we are here. So if I promise to make the class after spring break shorter, but as much as I'm making this one longer, can I keep going until we get our glorious result, which will take 5 or 10 minutes?
Yes.
Can I do it? Can I do it? Can I do it?
Practice doesn't start at 5 for me today.
Okay, cool. Let's do this. Let's do this. Let's do this. If you have to leave, you have to leave, but you can watch the glorious video. The video. The video. Yeah. Okay. Let's do this. Let's do this. Okay. So, I'm going to erase this because I'm still going to make comments on that, because I can't stand the thought of we come back from break and it's like you have no idea what I'm talking about because you didn't fulfill your break resolution of reviewing the notes before the next. Okay, shut up and do it so we can do this. I'm talking to myself and I said shut up. Okay, so from the equilibrium condition, again, G big M little m over R naught cubed is equal to 4 pi R naught P naught. In other words, it was GMM over R naught squared was equal to 4 pi R naught squared P naught, and I just divided through by 1 power of R naught on both sides. Right, if I multiplied this through by R naught, I'd be back to GMM over R naught squared, the gravitational inwards force, equals 4 pi R squared P naught, the pressure outwards force. And so, so we can say m d squared of delta R dt squared is equal to 2gm little m over R naught cubed delta R plus 2, wow, I'm really hating the chalk now, 2gm m over R naught cubed delta R minus 3 gamma times 4 pi R naught P naught delta R. Okay, I give up. I can't use my holder anymore. 3 gamma times 4 pi R naught P naught delta R. In other words, what I've done here is to use that 8 pi R naught P naught is 2g m little m over R naught cubed, so that I can have the same thing in front of the delta R terms here. These two delta R terms, I can put the same thing in front of them, in other words. And here, I replaced delta P with, and I erased it, delta P with what I had before, right? It would be R naught P naught times 3 gamma. So that I could rewrite all of this using those two substitutions like so. In other words, now everything's in terms of delta R. Before it had both delta R and delta P. Now everything's in terms of delta R. I've eliminated delta P so that I can figure out what happens when I change delta R. Or when I change R by delta R. So, put them together, and what do you got? Quick, what's 2 plus 2? 4, very good. I'm dealing with genius here. And so this can be factored into minus 3 gamma minus 4 times g m little m over R naught cubed times delta R. What miracle did I do there? Let's see. Oh yeah, it's this piece right here. Yeah, right. It's like for a second I'm like, wait, what? So, right, there is something, right. So 4 pi, yeah, and then here again, this is going to turn into g m little m over R naught cubed. I'm going to make that substitution as well. So it's a party. Everything's got g m little m over R naught cubed. And these two terms produce a 4 in front of that times delta R. Minus 4 is 4. These two terms produce a 4. And this term produces a minus 3 gamma in front of GMM over R naught cubed delta R. So in the end, in other words, d squared delta R dt squared is equal to the right-hand side there, minus 3 times gamma, minus the quantity, 3 gamma minus 4, GMM over R naught cubed delta R. This is what we've been waiting for, even if you don't recognize it yet, because this says d squared something dt squared is minus something times that thing that we're taking the derivative of. Yes, question?
Why did we drop the m on the left side?
Because I forgot to take it away on this side. Thank you for pointing that out, yes. Yeah, because little m is in every term now, so it can just be canceled through. Which is good. The mass of the shell doesn't play any part in this analysis. It wouldn't matter what the mass of the shell was. So thank you for pointing that out, yes? Okay, so if I have a harmonic oscillator, its equation of motion is d squared x dt squared equals something times x. What's that something in terms of the natural frequency omega naught? Do you remember? Anybody remember? Yeah.
Sine of omega naught?
No. That's when you get the actual equation. I mean, the actual solution. But the equation itself that's a solution of is that. d squared x dt squared is minus omega naught squared x. Having prompted, does that look familiar? Right? And then the solution is, a sine omega t plus b cosine omega t. Or a cosine of the quantity omega t plus phi. You name it, right? Is the equation of, what's that the equation of? The equation of simple harmonic motion, right? Right? So, look over here. If this overall is a positive quantity, then delta R oscillates harmonically, and omega naught squared is everything I just circled in that case. And that we get stable oscillations. The star isn't going to crush itself or anything like that. If I squeeze it, it'll push back. Pressure will rise more than gravity, and it'll start expanding again. But then when it gets past the equilibrium, gravity will be bigger than pressure, and it'll slow down and fall back in again, overshoot the equilibrium again. It will execute harmonic oscillations. What's the condition that all this stuff turns into a positive quantity? Well, it's that 3 gamma minus 4 is positive. Right? If 3 gamma minus 4 is positive, is G positive? Is M positive? The mass is M, yeah. Is R naught, the equilibrium rate, positive? All this stuff's positive. Is 4 a positive number? Typically, right? So 3 gamma minus 4 greater than 0 gives us oscillations. If 3 gamma minus 4 is greater than 0, in other words, if gamma, the polytropic index, is bigger than 4/3, we get SHM with omega naught squared equals 3 gamma minus 4 times GM over R naught cubed. Our star will be stable if the gas is a polytrope with polytropic index greater than 4/3. If 3 gamma minus 4 is less than 0, in other words, if gamma is less than 4/3, then what happens? Then we've got d squared x dt squared is equal to plus, let's call it, alpha squared x. What kind of solutions does that have? Think of how many of you have taken differential equations?
N pi x.
It's going to be, so it's going to be an exponential function. It's going to be like e to the plus or minus alpha x, right? You can have e to the alpha x times some constant, e to the minus alpha x, right? Because if I take one derivative of this, I get alpha e to the alpha x. And if I take two derivatives, it's alpha squared e to the alpha x. In other words, alpha squared times what I started with. E to the minus alpha x, one derivative is minus alpha e to the minus alpha x. Two derivatives is minus alpha squared e to the minus alpha x. Alpha squared e to the minus alpha x, right? So exponential solutions. If gamma is less than 4/3, we get exponential growth. Because in general, the solution will have a decaying term and an increasing term. But when you put in the initial conditions, you're always going to have at least a little bit of the growing term in there. And so what that says is that if I squeeze the star, instead of pressure getting bigger than gravity and it pushes back out and re-expands again, and then vice versa when it overshoots the equilibrium, if gamma is less than 4/3, if I squeeze the star, pressure rises less than gravity increases. If I squeeze the star and the gravitational force on the shell increases more than the pressure force does, it's gonna keep on shrinking and getting smaller and smaller and smaller in that case. We get exponential growth of the perturbation. So if we squeeze the star, squeeze! Because it's our BFF, so we want to give it a squeeze. Oh, sometimes love is destructive. If we squeeze the star, it collapses. It collapses. So we've reached where we want to be. For a non-relativistic white dwarf, what was the polytropic index? 5/3. Is that more than 4/3? It is. So is our non-relativistic white dwarf stable to perturbations? If I squeeze it, will it bounce back? It will. This is saying if gamma is more than 4/3, it's stable. You squeeze it and the pressure beats the gravity and it bounces back again. What about our relativistic white dwarf? What was gamma? Ooh, ambiguous. We're on the borderline case in that situation. And in fact, if it's 4/3, what this says is I squeeze it and nothing, right? This becomes just 0. It's styrofoam. I squeeze it and it just gets smaller and just stays there. Okay, this is where we'll be after spring break because, okay, just to state it quickly, but really, gravity is described by general relativity. And in general relativity, all forms of mass energy are sources of gravity. And in particular, pressure is a source of gravity in general relativity. In Newtonian physics, only mass produces gravity. But in GR, there's a term in there that includes the pressure. We'll see that when we get to cosmology. It'll be very important in understanding how the universe works, that pressure gravitates. And so what happens is that even though our analysis predicts that it would be just neutral, that gravity and pressure would stay in equilibrium when I squeeze it, they both increase by the same amount. Oh, but wait a minute, really that extra pressure produces some extra gravity too, so gravity ends up winning. And it would actually collapse with a polytropic index of 4/3, which means that it'll collapse a little bit before that, it turns out. And so when the white dwarf's electrons become relativistic, it's no longer stable. If you were to squeeze the white dwarf even the slightest bit, you would cause gravity to become stronger than pressure, and it will collapse. And that's the key behind the Chandrasekhar limit, is that you can't squeeze it and have pressure keep up with gravity because the electrons are relativistic. So bye-bye. And also bye-bye. Okay, thank you for this extra time. I owe you 15 minutes on the first class after spring break.